Okay. Sorry, I skipped the first slide. The first slide was whatever. It was the opposite of this. So NH4 is a plus. Okay. In water, what is it looking for? It's looking for a minus. So it makes NH4 OH. All right. And then what's left over? H plus, right? Seth wants to learn. All right, look. If the H plus concentration went up, what happens to the pH? It lowers it or makes it more acidic. Now, most metal cations, which are hydrated in solution, also lower the pH of the solution. The exception to that would be the cation of a strong base. So, oh, how did I bump you? I apologize. So like Na plus, it would make NaOH, but we know what about NaOH? Do we know anything about it? We know it's a strong base, which means does Na plus bond with OH in solution? No, it means it stays apart, right? So Na wouldn't do it, but most metal cations, so like here I have Al plus 3. All right, we're going to put it in water. It is not a strong base, or sorry, it's not the conjugate of a strong base. So it will go out and it will grab hydroxide and form a precipitate. All right, and what's left over? H plus, which makes it an acid.
Wait, so you could just pour aluminum ions into water and it makes a solid?
It forms a precipitate and makes the solution acidic, yes. Yes, acidic means it's making a lower pH. You okay with that? I'm good with it. Okay. Now, for video purposes, we started here and we said the same idea for anions. The X minus would go react with water. That should be up here, but whatever. It would form HX and leave excess OH minus, which means we would make a base. We talked about that, but if you're watching the video, I forgot to start before then. Okay. This one, don't stress as much for, but attraction between non-bonding electrons on oxygen and the metal causes a shift of the electron density in water. This makes the OH bond more polar and the water more acidic. Greater charge and smaller size make a cation more acidic. So the first two sentences, I wouldn't care much about the why, but I would absolutely make sure you know this statement right here. The greater charge and smaller size make a cation more acidic. That's because it's more attractive to OH minuses. So you could be given a list. So like A, B, C, D. And it might ask which cation would cause the solution to be more acidic. And you have like Na plus, Ca plus 2, Al plus 3, and like Pb plus 2. And which one would you choose? C. You would choose C. How come C? Greater charge. All right, what if this said Ga plus 3? Why would you still choose aluminum? Because it's smaller. Okay, we kind of all right with this? Because it grabs more OH. This is going to grab 3 OHs. This is only going to grab 1, and both of these are strong anyway. So they're out of the question. PB, it still grabs it, PbOH2, but it doesn't grab as many. So it doesn't have H plus go. What's that?
What does it have going for
The smaller the atom, the more I'm gonna lose my mind. You guys need me separated?
Yeah. Are you talking about second Lisa?
No. The smaller it is, the closer its nucleus is to the outside electrons, which makes the hydroxide more attracted to it. It's like from chapter 7 a long time ago. It has a greater nuclear charge. Yep. That was a long time ago. Okay. These sentences, I should say, are of utmost importance. Yep. Oh. What's that? Okay, well, I don't approve either. What I do approve is learning this stuff right here. This will 100% be applied in chapter 17. This will be fun. Sorry. All right. This picture illustrates this sentence right here. Right down here. So all of these are nitrates. So like you really got to think about the chemistry here. All of them are nitrates, which means all of them completely dissociate, right? So if you add NaNO3, really you're adding Na plus and NO3 minus. You okay with that? Now, what we care about here is the secondary reaction, and that is, does NaOH grab OH minus, and Na plus grab OH minus, and does NO3 minus grab H? And the answer to both of these are no, because both of these things right here are strong base and strong acid. So in this picture right here, when we add NaNO3, which really we're caring mostly about Na, the pH stays neutral. Right, because Na will not grab OH and H plus will not grab NO3. So everything that was there before stays there. It just turns salty. All right, now we have Ca involved here. Ca is not much more involved in this process. We have Ca, oh, come on. And then we have still HNO3. We're going to have HNO3 in all of them, right? And we know that won't matter. So I'll quit worrying about that. So calcium, it's the strong bases are family 1 and heavy family 2. So calcium is just barely the weakest of the strong acids. So it kind of grabs hydroxide to make CaOH2, but almost not at all. So you can see that the pH was slightly affected by adding calcium, but not much. It's still 6.9. But now zinc, we add zinc to this. The NO3 we don't care about. So now I have Zn plus 2, which we're wondering now, is zinc hydroxide going to form a base? So the question is to know if zinc hydroxide is strong or weak. And have we memorized that one? No, that means it is weak. So it will have an effect on the pH, and it went from 7 to 5.5. You would never have to know this with only this much information. Like you'll have to eventually calculate this, but you'll have way more information. All right, that's weak. The final one, we have aluminum nitrate. So we have Al plus 3. It will find hydroxide. In fact, it finds 3 of them. Is aluminum hydroxide a strong base? No, it is weak. So it will affect the pH even greater for both the reason that aluminum is smaller and that it has a greater charge. So it needs 3 OH minuses to every one. Yep, both of these reasons. Right. So the smaller and the more charged it is, the more acidic it is. Okay. So we would have never really thought before today that just adding something completely not acid or base can make something a base or acid, but we really can. All right. Oh, that was fun. What is the pH? Why do we need to do this? This is just a plain boring pH. I don't know. Let me get rid of that. All right. Now, I have said this, but let's make sure that we got it. Thank you. Olivia Lyman, not here. Sorry. Oh, she is? Oh, we'll leave it on her desk then. I'm going to finally move away. I keep hitting your knee and it feels strangely awkward. Did you just start to whisper?
I've been whispering this whole time.
I know. Oh boy. Okay. Cations of strong stuff will not affect the pH. If it ever says strong anything, it's not going to affect the acidity or basic nature. Other metal ions will cause a decrease in pH. Once again, this is just a summary. We mean more acidic. I keep saying that because a lot of kids think a decrease in pH means it becomes more basic, which that's super not right. When a solution contains both the conjugate base of a weak acid and the conjugate acid of a weak base, the effect on pH depends on the Ka and Kb values. This you don't need to stress about yet. Okay, like I mean yet. This is all chapter 17 right here. We call them buffers. And yeah, if I had something else, then we'd have to look at their Kas and Kbs and compare them. And we're going to do that. We're going to do that a ton in chapter 17. All right. Now, yes, sir.
So when it says it will increase the pH, does that mean that it's going to go, the number will be lower?
Nope. that means it will be a higher value or more basic.
Oh wait, I read the wrong thing. Sorry.
So that's all right. When it talks about pH, it really means the number from 1 to 14. A decrease going closer to 1 means acid. An increase in pH would mean closer to 14, and that'd be moving basic. People do get this wrong all the time. Okay, this next probably 2 slides, a bunch of slides. Yeah, you hope you're ready. They're not that bad. Okay, these things are not normally tested, and they're not on my test, but I'll just say them real quick. The more polar the HX bond or the weaker the HX bond, the more acidic the compound. Now, what that means is how do I put this in a simple way? So we're talking about the movement of electrons that are going to attract an H to stick to it or to give it out. If H is ever changed, you're going to have either more acidic or more basic. All right, acidity increases from left to right across a row and from top to bottom down a group. I would not stress about this, but I would for sure know that like over here, these things when added make things acidic and these things make things basic. Whoops. So, okay. You are. So I don't know. Don't stress too much about this slide or the next couple. In oxy acids, in which OH is bonded to another atom, Y, the more electronegative Y is, the more acidic the acid. So it's like, what are you talking about? These are all at oxy. Come on. These are oxy and ions because they have oxygen in them. This is the Y, these things that just said. Since chlorine is more electronegative, it's a 3.0, it has a greater Ka than like HIO, which has a smaller one. So if it gives you a list of iso, oxy, and ions, meaning they're all the same numbers, you have to look at which one is more electronegative. And they just are F, Cl, Br, and I. Electronegativity increases that way. Once again, very rarely, if ever, tested. All right. This one's more commonly tested. For a series of oxy acids, acidity increases with the number of oxygens. So the difference here, we're not switching the central atom, we're just adding oxygens. We've memorized these two strong acids, HClO3 and HClO4, but we didn't memorize these two. And that's because the acidity got stronger as we added oxygens. All right, this is a ton of fun. All right, resonance, not tested. Lewis acids, just for your information. Lewis acids are different looking than any other definition of an acid we've talked about. Lewis acids are defined as electron pair acceptors. So this would be a Lewis acid. Now, does anyone remember back in the day, what is unique about BF3? All right, bromine had the fluorine, and the fluorine, but it needed 2 more pairs, right? So if it can find something like ammonium that has 2 pairs and they can combine, life's a whole lot better. Okay, atoms with an empty valence orbital can be Lewis acids. Now, Lewis acids are not, these were not there, remember. Lewis acids are not very common. I mean, they are common. There are atoms on there, but like the application of them is extremely rare. Lewis bases are defined as electron pair donors. So this donated the pair, boron took the pair, life's great. Anything that could be a Bronsted-Lowry base is a Lewis base. Lewis bases can interact with other things other than protons, however. So protons are the H plus. So they can, like, there's no H plus here. Now I'm hitting someone else's knee. I need to just, I'll just teach closer here. All right. So these behave a lot different than we're used to. But don't really worry about these. Worry about the other ones the most. All right, we already did this one. Have we done this one? Yeah, we have. Yeah, we've done that like 3 times. Did we do this one? Yeah, we did this one. I remember because I typed this one, remember? Oh boy, what happens when that goes that color?
We just.
Uh-oh, oh no. Whew. Oh.
We are almost done.
All right, we're done. I don't know if that's how you spell no mas. All right, that is chapter 16. How fun was that? I enjoyed it thoroughly. Oh, my hips. All right. So if you haven't paid attention, you might not know, but chapter 16 and 17 tests are combined, remember? Let's see here. All right. Just checking on that. Let's get this going here. It looks like last year we finished this on April 7th. We're ahead of that, hopefully. Well, it was when we ended chapter 17. We still have 80 something slides to go here. Oh, we took a break like 2 days last week, didn't we? Yeah. Plus you have a break Thursday and you have a break after the second, a long break. A lot of you will never take chemistry ever again. There's 2 chapters after this is all. We skip 18.
So 17, 19, 20.
That's it. That's it. No more. Okay. Let's do it together. Here we go. You ready? You don't have a choice. Additional aspects of aqueous equilibria. This is not bad. Chapter 17 is all about what we call buffers. Now, this is risky because I don't really know biology very well, but can someone tell me about the carbonate, bicarbonate buffer system in your blood? It keeps your blood at the right pH. Okay, now I'll get there, but think about this. We have carbonate, and I could be even calling it wrong, but I'm pretty sure it's close enough. Carbonate is CO3, and it's a -2, right? And I said, what else? Bicarbonate, which I'm pretty sure is wrong. I think it's just hydrogen carbonate. Yeah, if we added the acid to this, we'd be in trouble. Okay, good. In your blood, and listen, I'm not a biology teacher, so don't at me. I don't even care if I'm wrong, but I'm close enough. You with me? Your blood. Your blood has to be a very specific pH. But have you ever taken an acid in your body? Yeah, I do it all day, every day. All right? I don't take as much base into my body as I do acid, but I could. In your blood, you have both of these substances. One of them that if it's in here and there's excess H plus, it will bond with this. And another part that is in your blood that if there's excess OH minus, it will bond with this.
Wait, so it's like your body uses the equilibrium constant and like you're able to not die.
Exactly. So we don't need to test on it. I don't know how that works out. Your body's doing it. Okay, so we're going to get to it, but a buffer is something that's really good at maintaining a pH because it has the ability to either accept H plus or to donate H plus. It can go both directions. Okay. I remember the most common base that I don't personally, not judging if you do, but alcohol is the base that you put into your body that your blood definitely has to account for. And if you put too much in, it'll kill you, right? You overwhelm the system, you change every way that your body processes things. And if you keep on going, it will kill you. Like I could. Our bodies are way better at dealing with acids than they are bases. So hold on. Yes, technically speaking. But I'm pretty sure our bodies are smart. Your body would throw up before it got to a critical level. And same with alcohol. You usually throw up.
Is that why you can't drink more than 10 minutes?
No, that has nothing to do with it.
You cannot.
Okay, we're wasting time. They're not related.
No, you said anything about throwing up.
Right. I would guess it's the volume. I don't know.
It's not the volume. You drink that much water.
I have no idea. But I'm going to move on.
We're doing the quick time.
Okay. It's of absolute importance to all of chapter 17 that you understand what's called the common ion effect. This is like, it's called additional aspects of aqueous equilibrium. I would just call it buffers, personally. Okay. The common ion effect. Please stick with me. Considering this equation, we have acetic acid plus water goes to hydronium plus acetate. Now, this is a weak acid, so it doesn't do this very much, but it does it enough that we know like vinegar has a certain pH. This is vinegar. If we increase the acetate, then Le Chatelier's principle says we move this direction. You okay with that? If I increase the acetate, I move left, which means what happens here? What happens to H3O or H plus? It goes down, which means what happens to the pH? It goes up. Less H means higher pH. So we had an acid, and all we do is add a salt or a common ion. The ion was acetate. So if I come along and I add NaC2H3O2, I add a common ion, the pH changes. You kind of with me so far? Did you say no?
I'm not sure.
It made sense at like the first 3 seconds.
All right. Let me get rid of all this and go back to what I had drawn.
Wow, this makes a lot more sense than the other one. You don't understand this?
Me?
This looks like you haven't seen it for a while.
I have seen it. I looked at it a year ago on the 7th. No, I definitely understand it. I'm just saying, do I want to draw all this out yet? And I might as well. Okay, so this is our common ion. We added it. That caused this to do what once again? Go down. So now in my solution, what do I have in here? All right, I have HC2H3O2. What else do I have in there? All right, I have HOH. What else do I have in there? I have some C2H3O2 minus. You with me? Okay. So in here, and I do have a tiny bit of H plus and OH minus, but a real small amount. In here, I have something that could donate an H plus. I have something here that could accept an H plus. If I have something that will absorb any H plus I add to it, or neutralize any OH minus I add to it, I'm going to have what we're going to call a buffer. It has the ability to do both. So think about this. If I come along and I add HCl, we know Cl is the conjugate base of a strong acid, so we don't care about that one, right? So if I add HCl, I'm really just dumping in H plus. Well, H plus is going to react with any acetate ion to form HC2H3O2. So instead of my pH skyrocketing when I added H plus, it goes up a little bit because I have the ability in here to accept H plus. Now I come along. What's that?
So it's like fighting against itself to make more.
Yeah, if you want to put it that way. Now, if I add NaOH in here, we know that Na doesn't matter because it's the conjugate of a strong base, correct? So I'm adding OH minus. OH minus will take any of these H's possible, but it will let it have to make HOH. So even though I added hydroxide, the pH doesn't plummet. I said this backwards, huh? No one called me out on it, but whatever. The change is small. I said it backwards. But either way, the change is small when I have both the ability to neutralize an acid or neutralize a base. This picture first, if you don't even know what I'm talking about, I added hydrogen first, so I should have said the pH didn't go down. It just went a little bit. The second one, I added base, so the pH didn't go up. It only went up a little bit. That's all. I just said them in the wrong order. Okay. Yep. We'll find out. We got a ton more slides to go.
Yeah, I am so confused.
We're getting there. Okay. So the extent of ionization of a weak electrolyte is decreased by the adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. So what this is a ton of words, but it's saying I can make less acetic acid dissociate if the solution already has C2H3O2, because it would go to H plus plus C2H3O2 minus. But if there's already a lot of this, very little of this will break apart. And I know you're like, what the freak, he's talking a ton. If we are adjusting any of these things, we are changing the pH. We're changing the pH. So if we add a common ion, we will affect the pH and give it the ability to do what we call this buffering action. All right, so let's talk about this common ion effect. We have HF. First off, strong or weak? Weak acid. We're adding it to water. So far, okay. Some of it breaks into H plus and F minus. How much? Not much at all. You with me? All right. So because HCl is a strong acid, it is also present. Hold on.
Where is HCl?
It just happens to be there. Like it's in solution.
So yeah, there should probably be a sentence somewhere that says we're adding HF to an HCl solution. Now it's here. It's telling you you have an acid here. This is bad. There should be something that says you're adding HCl or HF to an HCl solution. The key is that it's already here. So we have this weak that we're adding to a strong. So initially, my HF was 0.2. This is the same exact thing we did last. If we just had that, we just say x squared over initial equals Ka, and we move on with our life. You with me, sort of? Okay. So this time, we're adding it to something that already had a strong acid in it. So there's H plus present. The F minus was 0. Okay. When we get to equilibrium, we know that the concentration will change minus X of my weak acid. Some of it dissociates, and we call that X. So at equilibrium, my HF concentration is 0.2 minus X. But we've been assuming this entire time, what?
That's really small.
That it's really small. Okay, this time there was already some of this present. You kind of with me? Because it was in an HCl thing and we added HF. So now I have 0.10 plus X, and X is small, so we say it's essentially 0.10. Well, let me get rid of this. Hold on. And then this one is X. So now I would say my Ka is equal to 0.1 times X instead of X squared over the initial, which was 0.2, because we're talking about this part, the HF. All right. Now, this is going to change the Ka. What's that? It's not X squared anymore because we have some initial. When we change Ka, we've changed X, we have a different pH. I don't remember this. I think it's 1.8 times 10 to the negative 5 equals 0.1x over 0.2. Someone solve for X here if you would. You don't have to all do it, but multiply by 0.2 and then divide by 0.1. All right, anyone have a value for X? What's that? 10 to the negative 8? Fifth. Okay, now take the negative log of that number. Okay, we have 4.44. Now, if you would, someone calculate 1.8 times 10 to the negative 5th equals X squared over the initial, which was 0.2, right? and take the negative log of that.
Oh, is it negative
2.7. All right. Now, that was a bunch of math and a bunch of slides, but I want you to think about what we're saying here. The common ion effect. If we put something in that can react with the acid, we have a much more subtle change in our pH than if we didn't. That's the fundamental thing. If you didn't understand anything so far, are we about out of time? I guess we are. The main thing you need to realize is that if I add, this could be NaF, it doesn't even have to be HF. If I add an ion to this acid, it will affect the pH. It will make the changes more subtle. Okay, so a common ion will affect the pH in a way that it makes it more basic if you were making an acid, or it makes it more acidic if you're making a base. And Burgraph's already out there, so let me stop this real fast and we'll carry on tomorrow.